Okay, picture this. You're sitting in a taxi, stuck in absolute bumper-to-bumper traffic. You aren't moving an inch, but you can hear that meter up front, click, 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 charging you for every single second. Well, that is exactly what running a multi-agent AI architecture can feel like if it isn't optimized properly. Every single interaction consumes tokens, and if you aren't careful, your computing budget gets completely drained before you know it. So, welcome to this explainer. Today we're diving into a really phenomenal guide from KDnuggets by Yvonne Palomares-Carrascosa, and we're going to learn exactly how to stop that meter from running wild while actually speeding up your AI systems at the same time. Here's our quick roadmap for today. First, we'll look at the multi-agent cost trap. Then, 4 token-saving strategies, a deep dive into semantic caching, smart tooling and routing, and we'll wrap up by seeing the strategies in action. All right, let's jump straight into Section 1, the multi-agent cost trap. If you've been building or scaling multi-agent systems, you have probably hit this exact wall. You're left wondering, why do these architectures drain computing budgets so insanely fast? You string a few agents together to cooperate on a cool workflow, and suddenly, boom! Your costs are through the roof, and your execution speed is just dragging. It all comes down to something called token bloat. It's like a giant snowball effect. Your agents are constantly passing all these memory logs back and forth. They're loading up highly detailed tool specifications for every step. They're rereading massive system instructions every single turn. Every time your model processes these repetitive elements, that taximeter ticks up. It's incredibly expensive, and it fundamentally drags down the speed of everything you're trying to do. But hey, there is some really good news here. Let's move to Section 2, 4 token-saving strategies. The KDnuggets article gives us 4 core best practices to streamline multi-agent solutions. We've got static instruction caching, semantic caching, just-in-time tooling, and task escalation. Let's break these down, starting with the first one. Strategy number 1 is static instruction caching, or prefix-match caching. Think of this as the ultimate don't repeat yourself rule for AI. Large language models waste a ton of processing energy rereading the exact same long system prompts, basically the how to act as this agent manual, over and over again. Prefix caching solves this by storing those static instructions as key value pairs ahead of time. So instead of reading the entire manual from scratch, the model just opens up a summarized bookmark and goes straight to processing the new prompt. This slashes your preparation latency and massively cuts those token costs. Now let's skip over to the third strategy for just a second. Just-in-time tooling, also known as lazy loading. A super frequent pitfall when building agents is front-loading the context window with every single API, tool, and database schema available. That is a guaranteed recipe for bloated, noisy prompts. Instead, just-in-time tooling just hands the agent a lean, high-level directory of its capabilities. It only fetches the detailed, fine-grained instructions for a specific tool when it actually needs to use it. Make sense? Okay, those are fantastic structural strategies. Now, for Section 3, we're going to do a deep dive into semantic caching. To really grasp semantic caching, we first have to talk about embeddings. So, what are embeddings? Simply put, they are numerical, vector-based representations of text that retain their semantic properties. In plain English, it's basically how a computer understands the actual meaning and intent behind human words. It turns text into mathematical coordinates on a map so the system can quickly identify if it has seen a similar intent in the past. And this brilliantly illustrates why that matters so much. Look at these 2 prompts. How can I reset my router versus what are the steps to restart my Wi-Fi box? To a rigid old-school search engine, those use completely different words. But through embeddings, the system instantly recognizes they have the exact same intent. Semantic caching uses this intent-based recall. Think about it like an experienced clerk at an FAQ desk. If an AI agent has already solved this exact problem today, why on earth would it generate a brand new response from scratch? The agent simply hands out the pre-written cached answer. So the absolutely crucial point here is setting a threshold for how similar those prompts need to be by setting a cosine similarity threshold. And in the source example, they use 0.90, which is 90% similarity. You can safely serve that cached answer. If the match is 90% or higher, you literally bypass the large language model entirely. 0 LLM inference cost and near instant latency. That right there is how you manage a budget at scale. Moving right along to Section 4, smart tooling and routing. So not every user prompt requires a massive, heavy-hitting, expensive model. An effective architecture utilizes task escalation to essentially triage incoming tasks. Notice here how simple tasks, things like formatting data, summarizing text, or just classifying intent, get routed straight to lightweight, often entirely free models that you can run locally. Meanwhile, your heavy, compute-intensive models, where token consumption really hurts your wallet, are exclusively reserved for complex tasks requiring deep reasoning and multi-step orchestration. All right, let's wrap this up with Section 5, the strategies in action. Having the theory is great, but seeing how the author, Ivan Palomares Carasosa, actually translates these concepts into Python code is where the rubber meets the road. In his implementation, he seamlessly combines semantic caching and model routing. To do this, he uses a free, local model called sentence transformers, specifically the all-mini LM-L6v2 model. This is the little engine that does the heavy lifting of converting the user's text into those embedding vectors we talked about, and it does it entirely locally and for free. Let's walk through the logic of his route and respond function step by step. It's a beautifully simple flow. Step 1, you convert the query to a vector. Step 2, and here is where the magic happens, you check the semantic cache. If the similarity is greater than or equal to 90%, boom, you return the cached response immediately, totally bypassing the expensive LLM. If it's a completely new query, we drop down to step 3, route the task based on its complexity. And finally, step 4, save that new vector and the generated response straight into the cache for the next time someone asks. Let's see that step 3 routing in practice. Look at prompt 1, summarize today's server logs. The code sees the word summarize and notes it's under 100 characters, so it smartly routes this to the free local agent. Now look at prompt 2, draft an optimal 1-month itinerary for my upcoming Japan trip, taking into account documents, timetables, and real-time APIs. That is incredibly complex. The system recognizes this instantly and correctly escalates it up to the heavy-hitting orchestration agent. And this quote perfectly captures the core takeaway from the entire KDnuggets article. Scaling up and streamlining a multi-agent architecture doesn't necessarily entail escalated costs if you know how to properly implement these strategies. By utilizing static instruction caching, keeping your tools super lean with lazy loading, smartly routing your tasks, and leveraging the massive power of semantic caching to reuse past answers, you finally take control of that taximeter. So as you head back to your own projects today and start reviewing those computing budgets, I want to leave you with one final provocative thought. Take a really close look at your logs and ask yourself, are your AI agents actually thinking to solve new problems, or are they just expensively repeating themselves? Audit your token consumption, try implementing these strategies, and you might just find you can do a whole lot more for a whole lot less. Thanks so much for joining me on this explainer, and happy building.